So it's not good that there are no questions.
Well, I have a question.
Yes. Please.
I think Newton's laws might should be contributed by Galileo. This inertial ideas of inertial, and even the Newton's second law was already found by Galileo.
Okay, but by Galileo was earlier.
Yes.
And actually people attribute all this to Newton. Okay.
Yes.
So
Galileo have all this already. Yeah. Okay.
So the problem is not to attribute it, you see, and I will discuss Galileo too. The problem would be to, how to say, to correct it,
yes,
to make some sense out of it.
Okay.
So what, I'll be right back. You see, my explanation of these faults is confirmation of the thesis, not of the concept, that mathematician could not study physics at school, and mathematician could not study physics as a bachelor program. Because people are teaching this, not commenting that it is contradictory, not commenting that it is incomplete. Not saying that, so I will show you right now a corrected version, but people never say that Newton made a first approximation and then we will correct it. Mostly people do not say it, and it's a pity. Okay? It's really a pity. But also an explanation why mathematicians say, okay, I passed the exam on physics, I got this number of points, I entered the university, so now I can forget with this garbage. That just disturbs my sense of logic. And I will never, ever return to this. So, if you want to teach mathematician physics, you should teach them logical physics. And it is not Newton's physics, I'm sorry. So let's continue. Inspection of Newton's physics. So what we need to add is the Zeros Axiom. All bodies are made out of point-like particles. So if you have point-like particle, it means that has no rotation. It's one thing. Second thing, the line connecting two points is defined. Point-like objects that are called particles. So it means to make sense out of Newton's law, one has to assume atomic conjecture. So there is also, say, one prime axiom. Axiom 1 prime is body can be decomposed into the union of bodies. B1, B2. And 2 prime axiom. F equals to MA applies only to center of mass of a body. So it means that we do not know what rotation of the body is, but we have this consistency condition. And 3 prime if we have 2 bodies, then the force direction of the force lies in the cone. So this prime set of axioms is highly hard to apply, because you need to define forces for any ways how you cut a body into pieces. So it is very hard to check if the notion of force that you give satisfies these axioms. However, the prime set of axioms do not imply atomic idea. In this way, you can consider continuous bodies. So, people, Newton had to add either atomic principle or 0 prime sets of axioms. He did neither first nor second. In so-called theoretical physics, people use axiom 0. As I checked, in school, people mostly follow Newton, because using axiom 0 means a conjecture that everything is made from material particles that are point-like. Each of the piece of the axiom. However, people are afraid to attribute this to Newton. You see, at this moment, we see the complete inconsistency of this set of physics. Okay? So actually, in correcting Newton, I'll follow the first line. Namely, trying to make sense of what Newton wrote while he said that they were axioms, we need to make sense out of it. We will assume axiom 0. Okay? So there are point-like particles, and of course, point-like particles of finite mass. So in this model, all mass is concentrated at a point. Quite interesting observation. Otherwise, Newton's system of axioms just makes no sense, because nobody even tried to work out 0' axioms. So here we have actual point particles, and in 0' set of axioms, there are potential point-like particles. Okay. So in trying to save Newton, we have to rewrite things as follows. So there are point-like particles. That take value, their positions take value in the vector dimensional space, in the vector space, with the preferred coordinates. So I can add something and define the radius vector. And this is this. Actually, here I have to put module. And here I have to sum from beta not equal to alpha. So here is the world. Here are particles with masses m1, m2, etc. They are labeled as alpha, and this is the law. So Newton assumed that U that potential depends only on difference of inertial coordinates and also depends, it is a sum of pairwise potential. I can even put here alpha beta. So potential that would enter potential energy is a pairwise potential. Is a pairwise potential. This is inside the. This is the axiomatization of the Newton's definition of force. So when we look at real physics, we will see that not all forces are like this. In real physics, there is Lorentz force that is proportional to the speed. There is no such a concept here. Just Lorentz force contradicts the law. In Newton's mechanics, there is no place where you can add the velocity. So, let me continue with Newton. Okay, let us forget about real physics. So maybe Newton's axioms do not include real physics. Okay, but maybe in this way, this set of axioms is good enough to describe reasonable physical systems. So let me consider some examples of actual physical systems that do not obey these rules. Okay? Namely, let us consider a model. Let us consider a circle, S1 embedded in R2. So, and then let me assume that there is a particle attached to it that can move on it without friction. So no friction, no gravity. You may ask, so it is clear what is the inertial motion. You just give the speed v, and it moves with a constant speed. Inertial motion phi dot equals constant, where phi is the coordinate.
But there is
Yes,
no
yes.
force from the constraint. Why do you call it inertial?
Why? You see, it's because I am considering the physical world from embedding it in our world. So this is like people were doing in differential geometry. In differential geometry, people started describing manifolds as something embedded in R3 and then in Rn. Okay? Because in this way, they were sure that they actually exist. And in differential geometry, people invoked the concepts from Rn to define on a manifold. Maybe I have to say something about it. So differential geometry. You say there is a function. You say that the space is described by radius vector. That depends on some coordinates, phi 1, phi n. But this belongs to R and capital. So then it is easy to define, say, the notion of the tangent vector. Or tangent plane. You consider a plane in Rn that touches this, etc. So it's called external approach to geometry. So there is similar external approach to physics. Let us construct new worlds by embedding them in our world. That's why we will be sure that such worlds exist. And we understand what was the motion there. So I consider our world a circle and a point particle that moves along this circle. So this is a new physical theory that is obtained from our physical theory by just imposing this constraint that the particle is moving along the line. And we can easily realize it. So the law for a circle is phi dot equals to constant. So now let us play. So it's clear. And so there is an inertial coordinate. It's not a single value, but it's kind of an angle. And we can work with it. Moreover, in this world, we can consider two particles. We can connect them by a ribbon. And we know that potential would be K sine phi 1 minus phi 2 squared, maybe over 2. So it satisfies this axiom. Good. This world is good. This is Newtonian world. However, we may change this world a bit. Let us consider another.
What do you mean when you see that you attach a ribbon between these particles?
Here.
Yes. Does this ribbon go outside the border of the circle?
Yes. It's important that it goes outside the world of the particle.
But I don't get what's the point of doing this, because I don't see it from the potential functional.
From the potential, the length of this ribbon is sine phi 1 minus phi 2 over 2.
Okay, so this world, so in this way, this circle world, it is not the same as R quotiented by Z.
So in this way, you see, when I do it in this way, I know that the world with such potential exists.
Okay, I get it. Thank you.
So I know that it exists because I can create this world.
Yeah.
So I know that it is a reasonable world in physics. So it exists. This ribbon is just a way how I construct this world. So I am the God. I am constructing the world. This world would definitely have conservation of energy. So there is kinetic energy of these particles, there is potential energy, and this is a perfectly Newtonian world. So I constructed this model to be able to play with it. Okay? Now I'd like to change the circle into some curve, C. Now, still, even if it's a curve embedded in our three-dimensional space, I understand what the inertial motion is. It is the motion along this curve such that this is constant. Okay? Because it means that kinetic energy is constant. Now, I may ask if there is a inertial coordinate. And here the answer is yes. There are inertial coordinates. Very good. So my question number one about inertial coordinates was about the sphere. And here we have a line. And we have inertial coordinates. And these inertial coordinates are defined as follows. Let us pick the beginning and let us compute its length of the segment connecting the zero and the position. And this is an inertial coordinate that we will call, I don't know how to call it, phi. And the constant velocity just means that phi star is constant. So it is very preferred coordinate here. I mean inertial coordinate. Good. So we satisfy, in this world, we managed to satisfy the first law of Newton. However, let us look on the second and third laws of Newton. And here we will see surprise. Imagine that in this curve, we have a piece like this. So here we have pi over 2. And suppose that one particle is before the angle and other particle is after the angle. And let us assume that this distance is A and this distance is B. Let us assume that this corner is the zero. Okay, so here, of course, oriented length. So it could be negative, of course. So if I go this way, I have something positive. If I go this way, I get something negative. Now, what is the potential? K A square plus B square over 2. Okay? Because I have a ribbon here. Now, what are inertial coordinates? Inertial coordinates of first particle equals to B. Inertial coordinates of the second particle is, of course, minus A. So, phi 1 minus phi 2 is definitely A plus B. So, potential is not a function of the difference. U is not a function of phi 1 minus phi 2. So it already means that this is not Newtonian world. We can make contradiction even stronger. So what is the force? from particle, how particle 1 acts at particle 2. We need to take this thing and project. What is the opposite force? We need to take the same vector and project. So in one case, you have cosine alpha. In another case, you have sine alpha. So f, say 1, 2, is cosine alpha times f, say two-dimensional world. And here we have sine alpha. So forces written down in inertial coordinate system of action of 1 on 2 and of 2 on 1 are different. So, you see, I constructed the world with an inertial system such that for free particles, I have motion with a constant speed in these coordinates. However, with the forces that are not Newtonian, while this is quite a reasonable system. So would it be a circle? It would be okay. For different shape, it's not a. Okay? I mean, so you see this puzzle. So the set of axiom that does not include such natural worlds like this is just okay, has to be seriously corrected. So it means that already where we consider motions of particles restricted somehow, and actually it happens not in theoretical mechanics, it happens in mechanics of machines. It's very natural to have such things in machines. We cannot apply, so in machines, we cannot apply Newtonian rules. Or we can reformulate, or we have to reformulate it in external terms. Okay? So it's not good. So it means that to work with, say, machines, we cannot work on configuration space. We have to think how these machines are embedded in our three-dimensional world. Okay, when you work with machines, maybe it's okay. But it means that the class of theories covered by Newtonian laws is not big enough. You see, for a circle, it's okay, and for other figure, it's not okay. So, so it is a good reason to completely reconsider Newtonian system. So there is another reason why one has to reconsider Newtonian system. So here is the dependence of the potential on the difference of coordinates in inertial coordinates. There is another example. Another example is that now what we now understand as is potential does not necessarily depend on 2 points, on 2 material points. as an example, consider system of points connected by some ribbons. I don't know, something like this. You will have collective phenomena. So each point, so the force that acts on this point is not a sum of the force acting from this and this. Because there is, you see, there is something in the middle, and you need to take it into account. So how to formulate this mathematically? Suppose we have potential that depends on positions of the points on the pairwise, phi A, phi B. Let us call this U. Let us take extremum of U with respect to phi 1. And we will call it effective potential. For phi 2, etc., phi m. So here we have n particles, and here we have n minus 1 particle. So if we start with a pairwise potential and extremize the position with respect to one of them, the resulting potential would not be pairwise. So it means that the original axiom that bodies are acting on each other by forces, and these forces should be just summed up, is also non-valid. It is wrong in this mathematical context, and by the way, it is wrong in real life. Actually, as we will discuss later on, there is the gravitational potential. And you study at school that it starts with this, m1, m2 over r, 1, 2. So people study this at school. Actually, there are corrections to this potential in real life. So here is another constant, and here is m1, m2 squared over r12 squared, plus, of course, symmetric thing, m2, m1 squared, r12 squared, plus some other corrections that are even smaller. Okay? How do we know that such corrections really appear in physics? We know that by studying the notion of Mercury around the sun. 1/3 of motion of the Mercury around the sun is described by such term. Now, let us see what do we see, what do we get here? Why this term is so puzzling? So here is the sun, okay? Here is a small Mercury. let us divide sun by 2 parts. So here is the mass of sun over 2, and here is the mass of sun over 2. If according to Newton, force between sun and Mercury is sum from the force from the left half of the sun and the right half of the sun, the total force should be proportional to m sun. And it could not be proportional to m sun squared. However, we measure this. So it means that forces are not added. So conception of adding forces is a misconception. Okay, this misconception was allowed for Newton because he was genius to put forward some set of ideas, some framework. What I consider as a shame is that almost 400 years after Newton, people are not writing down what should be the proper corrections. And people still use this stupid notion of force that you can sum up, that actually has no meaning in the real physics already. Say nothing about model physics. So, if we are interested to teach mathematicians physics, we have to teach them honest physics, and not that. So, it seems, so one may think that we should invent some new physics, etc. No, we do not need to invent new physics, because actually this physics was already invented. Yes? And this physics that was invented.
So why we add forces?
Why we add what?
It's the reason why they are not the same direction.
Why we cannot add
this? It is because they are not exactly pointing to the same direction that we cannot add this.
No. So now you see, now the puzzle is that consider Mercury and Sun. So okay, Sun is almost pointless from this perspective. Sorry, it's not pointless, it's almost a point. So actually, if we say that the force between Mercury and the Sun is a sum of forces from half of the Sun, we can have the force only be proportional to the mass of the Sun. We cannot get such a term. We can only have linear proportionality. Because we can say, let us cut Sun into capital N pieces. Then the first term would be m Sun to the n times n. I'm adding the Sun. The second piece with square would be n m Sun to the n squared. So the second piece with the square of mass should be equal to the same thing but divided by n. It's impossible. So concept of adding forces just violates such piece. So after we see this piece in the effective potential, we should say, come on. Forces are not added. No. And later we will see that forces are not added in any. So there are many examples where forces are not added. I am giving you the example of Mercury. So this is a misconcept. So this misconcept happened because in real life, this term is much smaller than this term. Okay?
So the actual terms can really be measured by experiments, right?
So when I say measured by experiments, I mean the following. So would Mercury make a round motion around the sun? We would not be able to measure this. However, Mercury is moving like other planets approximately by ellipse. Okay? However, the ellipse would be a stable trajectory without this term. However, with this term, the ellipse is rotating a bit, and we can measure it.
Well, but you know, we can argue that we have other planets like Jupiter or something that has some perturbation to the terms.
So this type of perturbation is not allowed by Newtonian theory, by Newtonian framework of forces.
Right, but the point is, if you want to argue that in this way, the Newtonian mechanics is not consistent, that you need to be sure that this kind of terms really exist, right?
Yes, so these terms really exist in nature. In real nature.
Okay, thank you.
These terms do exist in real nature, and we can measure them.
Oh, okay, I see.
They were measured 100 years ago from observations at Mercury. Maybe now there are other measurements of this term, but at least they were measured. But you see, it breaks Newtonian framework of mechanics or the world. So that's what the message that I'm trying to give you. So it means, finally, that Newtonian framework has to be replaced by something. And we are lucky that people in 19th century found this replacement. And this replacement is called extremal action principle. So, go away with forces that we are trying to add. Okay? Forget about it. Suppose that we have configuration space. And this is some manifold. Now we are happy because now we could include rotation, because so-called orientation means that for a solid body, configuration space is R3 times SO3. So it's a manifold. SO3 is actually RP3 as a manifold. Okay? So now we have configuration space. Now we are happy to know that one can write down, one can choose any coordinates and write down Lagrangian depending on position of the particle, its first derivative, maybe its second derivative, etc. Integrated over time and take extreme. So we should be called Euler-Lagrange. Equations. So they're pretty old. But you have to do this in order to save Newtonian, not Newtonian, in order to construct what I would like to call classical physics. Something that mathematician can understand. Because the number of problems in Newton in this classical physics is much smaller. So people have to start with it. So the book of Landau and Lifshitz, on theoretical physics, starts with this. So I would like to say, all other approaches to classical physics are incomplete, contradictory, or wrong. This thing should not be simplified. Now, here this thing depends on say position of something in configuration space. If configuration space is really a space of the particle, we can and should add fields. So I explained the first reason why we need to do this. Second reason, adding fields. So fields are a piece of matter. We should admit it. And if fields are a piece of matter, we definitely cannot add fields into Newtonian formulas. They are not bodies at all. They have very different description. So when we admit fields, we should say goodbye to good old Newton. So we had a physicist Landau. Maybe you have heard about him. At least he got a Nobel Prize. And he was not polite. And he liked politically incorrect jokes. And sometimes he said that this theory has to be buried, you see, put it to the grave, but with corresponding honor. Okay, so I want to say that Newtonian physics should go to the library, to the history of science, somewhere, but it should not be presented to mathematicians. For all the reasons I gave and I tried to give, and I was trying to give. It was predecessor of what people call classical physics. Not classical physics at all. So the next time, on the physical form, I'll describe not precursor, but classical physics. Okay? So now you are ready to hear it. Unfortunately, even great Feynman, in his lectures on physics, was not pointing this out properly. So I cannot refer to him. But this has to be explained not in the course of theoretical physics, come on. This has to be explained at school. Okay? And if it is hard to understand, then the effort of the teacher should be spent not on set of problems people used to do with the machines of the 19th century, with blocks and all this. Blocks, bricks, etc. Come on. It's not contemporary science. It would be much better to explain the setup of physics. And this is definitely not Newtonian setup. Later on, general relativity was included here, but inclusion of general relativity in this formalism is not such a big deal, actually. But passing to this formalism from Newtonian picture is a major step one has to do. So if you don't know it, you have to study it, and I'll explain it. Okay, so in this way, we have to say goodbye to general physics. Okay, questions? It's the end of today's talk. So still, while maybe you are thinking of questions, and maybe you'd like to think about inertial coordinates on the sphere, I would like to say that my next talk on Thursday would be from mathematical hall. And please don't be surprised that I am changing languages. So at the beginning, I will talk in the language of physics on Tuesday, and on the language of mathematics on Thursday. So it's possible to speak both languages, and it's necessary if you are trying to do mathematical physics.
This classical physics of finite degree of freedom was clarified by Arnold in his mathematics of classical mechanics.
Yes. So we will come to this. So yes, there was the work of 1966 by Arnold, who embedded actually classical mechanics of particles inside the geometry. So, and also maybe of particles and fields. But for fields, it's something infinite dimensional. Okay, we will come to this, yes.
like to know where I can find reference of gravitation with the extra terms of higher order.
Okay, you should not look so in any book about in the Wikipedia, it's called the precession of Mercury. And we will come, and I think that in the so-called course of physics, we will try to derive this somehow. This or similar phenomena.
Okay.
Because because I need to make another step. I need to introduce fields. Okay, and when I will introduce fields, you will have the classical theory of particles and fields. And when we will do this, I'll explain the last goodbye from mechanical world, that is an ether theory that still can exist in dimension 2 plus 1. Okay, we will come to it step by step.
And also, I noticed that it is the Lagrangian, the L.
Yes.
That you have the second order derivative of phi and etc. But I remember from mechanics that we only use the position and the speed, and we do not have higher order terms. Why?
So actually, you see, when you say you mention from mechanics, so it depends who is writing down mechanics. Okay. So when somebody is writing a book, he says, by mechanics, I mean, and he says something. Okay. So you can define mechanics as something that doesn't have higher derivatives. However, it would not be that nice in generalizations.
And actually, I remember that when I was an undergraduate student, our teacher of mechanics, he asked us why do we consider only the position and speed and the acceleration, but we do not consider higher order derivatives of the position. And I was not.
So some people do, some people do not. So so again, it depends on the approach. So there is no limitations to consider this. Then you may ask, do we have a models where we have this term?
Yes.
And so there are models that are called theories with higher derivatives that people use in mathematical physics. So it's better to study mechanics here because it's not that different. Conceptually. So actually, later on, we would consider fields as such that mechanics would be considered theory of one-dimensional fields. And in this way, there are terms with higher derivatives. So these terms are used, so these terms are actually used in the so-called regularizations of ultraviolet divergences. And that's why it's better to think about them already in mechanics.
Mhm.
I mean, like, is it possible to do this? And what would be consequences of this? And so on. So you see, people actually consider mechanics not for mechanics. People consider mechanics as a model that one can develop further. You see?
Mhm.
So I told you that mathematical physics is dealing with the worlds, different worlds that are similar to our worlds or differ from our world in some parameters. Like the number of derivatives, it's also a parameter. Or if you wish, these higher derivatives appear if you consider, okay, let me tell you something. Alpha prime corrections to gravity that you are getting in string theory, okay? I don't know, would it help you? But there are quite popular models where such things happen. But it would be quite stupid to redefine things when you come to these models. It's better to deal with things at proper generality from the very beginning. And actually, this was a message of somebody who was teaching Landau. Actually, not Landau, it was another person who wrote this first volume. Landau just got it. So it's a long story. About Stalin, prison, and totalitarian countries, okay? Country. So I will tell you who actually wrote the first volume, okay? Is the year 1937. So I mentioned first volume of what is called Landau-Lifshitz theoretical physics. Okay.
Okay, so we'll continue on Thursday, right? 3 o'clock.
Yeah. Yes. So we will continuing on Thursday, and the topic on Thursday would be algebra geometric correspondence. Okay. Of course, you will get the abstract, but I'm telling you this in advance. What will be the title? And the next Tuesday, we will come back to physics, and so on, until we meet somewhere. Of course, it's a wrong definition, but what would you propose?
I guess like one thought would be if forces had some sort of typing system, so like in the examples you gave, the issue was that there was some sort of charge, and the center of charge didn't correspond with the center of mass, but the forces were aligned along like centers of charge, so to speak.
Okay, so in this way, you should say that you could not formulate things in terms of bodies. It means that you formulate things in terms of point particles. So the first message is there is no way to formulate the third law if you work with bodies, on the level of bodies. You have to assume a point particle structure.
But then you also said that we cannot add forces, but then how? What are we supposed to do? Isn't that contradictory?
No, it's not. You see, it's so. So I would like to say that the notion of force is sick. So we could, we could cure it a bit and let it move, you see, but we will not marry this concept, okay? So, that's what I say, that you can try to make something out of it, adding point particles. You should say that if the special case you have, for some reason, only pairwise potential that for some reason depends only on the difference of inertial coordinates that you for some reason have. You see, there are too many assumptions. Then you can save the day. So I want to say that this theory, you see, has limited area. It could not be a foundation. You could live with this theory for some time, but you have to change the foundation for many reasons. So I gave like 5 reasons why you have to leave this concept of forces. Okay, so there are old concepts, like, I don't know, sunrise, sun is rising. Everybody see it, but we know that it's an effective phenomenon. It's because the Earth is rotating. But we speak about sunrise, like Japan, country of rising sun. Okay. If you would like to understand the foundation of physics, we need to say goodbye to Newtonian foundation. So it's not foundation that we could use to construct theories. We have to change the foundation. And first change is the change from pre-classical Newtonian theory to classical. You see, it's much better. And later on, we will have to change from classical to quantum. But we cannot do it immediately, you see. Maybe even you could understand it, but you'll have hard time talking to other people. You see, the rule of this is not to say, let us throw this away. let us replace with something else. We would slowly analyze and replace. Okay? But I want to show you that Newtonian's picture. Okay? So Newtonian's principle, so if somebody would send Newtonian's principle to mathematical journal, it would be returned for the major revision. It would not be accepted, even as a model. So I was feeling this when I was a schoolboy, when I prepared to enter the university. That not consistent. So I am not afraid of saying this, you see. So when I was at the university, then when I was the second year, we have the subject called theoretical mechanics. And at the end of the subject, the teacher was giving a 1 hour talk. And then he said, you see, I derived the extremal action principle from physics. So you get it. But it's completely wrong idea. Extremal action principle is the proper foundation of physics. You cannot derive it from the restricted theory. So it means that this professor was not understanding the meaning of this principle. What can I say? It's a pity. And since I was at the best university in 80s in Moscow, I think that in many places people just do not understand what's going on. Okay. So now, you see, I know China. You will miss your dinner. I don't want you to miss your dinner. Okay? Yes, Newton's law of gravity is just a first approximation. First order approximation. When we will come to effective potentials, you will see how it happens. I just don't want to hurry up. Please note, I am not crazy. So I don't want to frighten you. Just please think about it. And if you just write me what you are thinking about it, what you think about this situation, write me. All your comments are very welcome. Written comments are even better, because I can read them and maybe we'll meet in the internet and discuss. Okay? So thank you very much. It's time to have a dinner.
Okay, so that's all for today.
I think that's